Howdy, hey, hi, Spaceman Josh here, and today I wanted to talk about how to search for exoplanets. Now, this is something that really interests me. It's actually one of the things I wanted to go into as a potential career, and so I had a lot of fun trying to do some research into this and just learn more about the different things that come with this. Now, before I jump right in, there is something I wanted to sort of introduce you all to that involves one of these methods for searching for exoplanets, and it's something called the Doppler effect. Now, the Doppler effect is sort of the change in frequency of a wave whenever the source of waves is moving with respect to the observer. And so that gave me kind of confusing, so I sort of had this little diagram thing that I drew. And sort of the idea with this is sort of if you have this blue dot as sort of the initial location, when we start looking at the object, it sort of emits a wave. And so the wave travels sort of outward in all directions at a constant velocity, sort of at a constant speed, and so then some amount of time passes, and now we're at the orange dot, and so the wave from the blue dot's expanding a little bit. The orange dot, now when we're at the orange dot, now the object emits another wave, and so that one starts to expand from its initial location as well, sort of expanding a little bit as time goes on. And as time goes on, we also move forward, and we get to this brown dot. So if we looked at the comparison of the waves after some amount of time at the blue dot, the orange dot, and the brown dot, we would notice that with the object moving, the green lengths over here between the blue and orange wave and between the orange and brown wave, compared to the purple waves over here that are actually really short, is that these green waves are a lot longer than the purple waves, and that's sort of the idea of the Doppler effect of sort of the frequency of waves is how often a wave reaches a certain location. So if you were standing over here, right outside this blue wave, you would essentially the waves would hit you a lot faster than if the object was just standing still. If the object was just standing still and emitting waves, the distance between the waves would be about the same distance as what this object is moving, what these two objects are moving, in a sense that it would just simply, they would be equidistant from each other, and they'd all be the same distance. Whereas for this one, they'd be the same distance on either side. That's the important part. Whereas for this one, for this situation, the waves over here are a different length than the waves over here, which are a different length than the waves over here. And that's sort of the idea with sort of the frequency and sort of the waves per second type of idea is sort of the way you can look at frequency in this case. And sort of when we talk about higher frequencies in terms of light, with higher frequencies we actually sort of call it blue shifting. So when something is moving towards us and the frequency ends up getting higher, like with these purple distances, when it's moving towards us, we say it's blue shifted. And when we have things are moving away from us, say we're over here and this object is moving away from us, the waves sort of get wider and wider than what they actually would be, and so we get a lower frequency that we call it being something called red shifted. If with light we call it being if something's moving away from us, we call it red shifted. And so that's actually this Doppler effect is how we know that the universe is expanding, because every galaxy that we look at, except for the Andromeda galaxy, is red shifted, and I do mean every galaxy we look at, and so the Andromeda galaxy is henceforth also it's the blue shifted, and we will eventually collide. And I may talk about that in a later vlog, but for now, just the idea of that's how we know the universe is expanding is because of this Doppler effect, and seeing that just about everything is red shifting from us. It's moving away. And so now that we sort of get an idea about the Doppler effect, I wanted to talk about how to search for exoplanets. Now, there are 5 methods that I was able to find on how to look for exoplanets. The first one is sort of watching for sort of a wobble. It's something called it's something involving the Doppler shift, or it involves understanding the Doppler effect. So if we have two objects, say a star and a planet, the gravitational effect that the star has the planet is very big. Sort of if this is a planet and this is a star, the force of gravity towards the star from the planet is very big. And so you end up, if you have the planet moving, you end up orbiting around the star. However, though, gravity affects all objects, in the sense that if the if this star is having a gravitational effect on this planet, that means this planet is having a gravitational effect on this star. It's not very big, and for most star planet systems, it's very minuscule and unnoticeable. However, the way that ends up working then is there is some effect where as the planet orbits around the star in a sense also sort of wobbles a little bit in its orbits, where it will have sort of this very minuscule, sometimes even just a lot of times unnoticeable sort of, here we go, unnoticeable sort of orbit. We sort of have it in the sort of, there's a little purple circle there to demonstrate the idea that they're very small orbits and it's very hard to be able to notice. But one thing with it is that means the star actually itself is moving a little bit. And so with stars, there are stars that if they're close enough to us, what we can actually do is we can measure the light coming from that star. And if the light gets red shifted, we know it's moving away. When it's blue shifted, we know it's coming towards us. And so if it goes between being red shifted and blue shifted constantly at some frequency, then it's sort of the idea that there's something orbiting that star that's having a strong enough gravitational effect to actually affect that star and to have that you do that red shift and blue shift. And that's one of the ways that we can find an exoplanet. And so another method is actually straight up just taking pictures. And so with visible light, we can't really do that yet. Hopefully the James Webb Telescope, I've heard, is supposed to be able to do that. It's a new telescope that's supposed to replace the Hubble Space Telescope. I'll talk about that in a later vlog. But essentially, the visible light, we can't really look at exoplanets yet. We can only just look at stars. And so however, with other types of light, like infrared light, and we may have a bit more luck. Say if we've actually had taken pictures where we looked at a picture of a star in infrared light, and then we took sort of a software to just cover up the light from the star, because of how enormous it is. And once we actually blocked that light out on the image, we actually found other objects that also were emitting infrared light, which we were able to deduce that it was an object orbiting that star. And sort of we were able to find an exoplanet by actually looking at the infrared light that it emits after sort of blocking out the infrared light from the star itself. Now, another way that we can able to find an exoplanet is looking at sort of light in a gravity lens. The formal name of this method is gravitational microlensing. And sort of the idea of if you have a star with a planet orbiting it, and then you have a different star that's farther away, and then when the planet with the star with the planet and the star it orbits, as it goes between the Earth and that far distant star, the light from the far distant star actually gets bent by both the planet and the star it's orbiting. And so while minuscule compared to the parent star, the bending of light that the planet has is still measurable with current technology. It's very difficult, but it's still doable. And so that's one of the methods we can look at trying to find exoplanets, and really just any object large enough to bend light, noticeable as for our current technology. If you wanted to find, just a humongous asteroid, if for some reason there was an asteroid that wasn't classified as an exoplanet that was able to bend light enough for us to measure it, then we could find that as well. It's the idea of there's an object that bends the light and we are able to detect it. Now the fourth method is called is sort of described as minuscule movements. It's formally called astrometry. And so it's continuously measuring the relative distance in the actual sky from one star to the next, and then watching for changes in the distance. It's similar to the idea of watching sort of for the wobble with the first method with sort of the Doppler shift. It's a similar idea in the sense that you are essentially you're looking at the star itself and watching how it moves, and sort of this idea of this diagram that I'm quickly drawing. Sort of the idea, if you have sort of this blue star in the middle, and you have these purple stars, and you have a known distance of these orange lines from the blue star to these purple stars, if the planet is large enough to make the star wobble a noticeable amount actually in our sky, then these orange distances would change. And so we can try and actually measure these distances and seeing if they're changing. And if there's a noticeable enough change, we can deduce that there's actually something moving the star, which is more than likely a object orbiting that star. And we haven't found a lot of planets using that method. It's actually it's not that efficient of a method, but we still have found at least one, and so it is sort of a method of finding of exoplanets. And so then sort of the final one I want to talk about is searching for shadows, or watching a planet transit a star. The essential idea is when a star has a planet orbiting it, the star, we can measure a certain an actual intensity of light that we get from that star. And so when a planet goes in front of the star relative to us, what can actually happen is there's actually a measurable, so if we have the intensity of light, there's actually a measurable dip as the planet goes in front of the star, and then it goes back up to normal once the planet is done transiting, going in front of the star. And so we can actually, using that method, we can actually detect objects orbiting a star by just looking at the amount of light that the star itself gives out. And what's interesting about that is there's actually a lot of things that we can get told from the transit of an exoplanet. And one of the really things I think is really cool is if the exoplanet has an atmosphere, and you look at the parent star through the exoplanet's atmosphere while it's transiting, the elements that make up that atmosphere, for the most part, can actually be somewhat measured through something called spectroscopy, and actually looking at the way that the light is affected at certain wavelengths as it travels through that atmosphere, and then coincidentally goes to and ends up hitting the Earth. We can actually measure at specific wavelengths what elements are present. What's interesting about the sort of spectroscopy is the way that we measure is something called sort of emission spectra. Every element has its own unique emission spectra, and so we can actually measure elements of we can measure certain things about an atmosphere of an exoplanet as the planet transits its parent star, which is actually really, for me, it's really cool and just phenomenal that we can actually do this. And so we can also measure the actual, if we know the size of the star, we can actually also measure the size of the exoplanet itself, with depending on how much the light goes down, how much the intensity goes down. We can measure how large the planet is, because there had to be a certain sort of, if you have sort of this star and you have a small object, the amount of surface area that star is, that this planet is blocking, would essentially, there's some measurable amount that is the surface area that it's blocking, so that there's mathematics to sort of correlate that with the amount of intensity of light that would be giving out. On top of that, if we measure the gap in the terms of how long that intensity was dipped, we can actually measure how close to the star it is, because it would also depend on how fast it's going. And if we know how fast it's going compared to the diameter of that star and all these other factors, we can actually measure how close to the star it is and how fast it's going, things of that sort. Which, with that can actually some pretty interesting results, because for example, the fastest recorded exoplanet is the exoplanet called C12_3474b. I'll go over naming conventions in a later vlog, but essentially that's what it's called. It's very, very scientific. So the orbital period of that planet is 6.7 hours, and so it's essentially, it goes around the sun, its parent star, every 6.7 hours. On top of that, it's actually about 3 times larger than Earth and about 5.3 times more massive. And we're able to tell all of this simply because of how it's transiting in front of its parent star. And what's really cool about that, and knowing sort of the relative size and mass to Earth, is you can actually I actually did a little bit earlier and looked at the formula for gravity. And sort of to look at the gravity when you ignore angular momentum, for simplicity, the gravity of that planet is actually about 59% that of Earth's. And so it's larger and more massive, but because it is the scale to it being larger compared to it being more massive, it actually has at the surface, while ignoring angular momentum, less gravity than Earth, which is an interesting concept in itself. And so that's all I really have. If you want to also check out some of this stuff for yourself, and actually NASA has a site that actually tells you these 5 methods and actually how many planets they have recorded using these methods. I'll put the link of the website in the description. Other than that, thank you for traveling with me today. If you like to, go ahead and hit the like button. If you want to see more of my videos, go ahead and hit that subscribe. You can also hit that bell. It turns on notifications, lets you know right when I upload. Other than that, thank you for traveling with me today. Spaceman Josh, out.